Hello, everyone, and welcome to my channel. This is Sohini from South Bay, California, and I welcome you today. So this is the channel where we talk about anything AI, and we do look at medical imaging use cases quite a lot, but computer vision, algorithms, code. So we talk about anything from devices, laptops to new algorithms and even research strategies. So today in this video, we are going to be covering a special topic which was requested by one of the subscribers. So thank you for reaching out with your wonderful questions in the comment section. So the topic for this video today is going to be MaskRCNN for instance segmentation. So what happens often is if you have images, you want to really know is how many regions of interest are there and exactly where are they located. For instance, if you take an image of your road outside, you might see that there are multiple cars, there are multiple pedestrians. So in order for you to gauge is there a traffic congestion or not, you might need to know how many cars there are and how many pedestrians there are. So whenever there is this need to count how many instances are existing in an image and exactly where they are located, we call it an instance segmentation method. And today we are going to be covering a whole code base on how to apply MaskRCNN specifically for instance segmentation. So for any of you who have followed my semantic segmentation videos before, this might be very useful as a new turning point. And then I am going to be releasing code with this as well so that you can try it on your data set. So if this is of interest to you, please give this video a thumbs up and subscribe to this channel. All right, so let's start with first looking at what is MaskRCNN and what is instance segmentation and how we can actually go about utilizing it. So first off, let's try to understand the why. Why are we covering this topic today? As you may see, as I gave you the example of a road with cars and people in it, the same way if you are taking a general countryside image, and here a typical classification problem would say this image has person, it has sheep, and it has dog. And now if you go into the object detection space, it will make bounding boxes in and around every sheep, every person, and every dog. So if you see the boxes here, they are color coded based off of the object type. So all of the sheep have the same color, the person has a different color, and the dog has a different color. And if you try to do semantic segmentation, like if for instance UNet, it will give you exact boundaries in and around, or fully convolutional networks as well, in and around each and every object of interest. Notice in the semantic segmentation, all the sheep have the same color because they will be extracted as a part of the same color plane. But now if you're trying to transition from semantic segmentation to instance segmentation, the major difference that happens is all the sheep, they are not the same color anymore. What happens is now they become a different class. All right, so every single instance is its separate class or category. The label of that category may still be sheep, which is given by your classifier, but you have to understand that now every single region of interest, every single sheep is a separate class altogether. So this is sheep 1, sheep 2, sheep 3, sheep 4, sheep 5. So every sheep is a different class altogether. All right, so that's the reason why there may be a need to count the objects and also locate the regions of interest. So where are the sheep located? Are they right about in the center? Are they scattered all over the place? For instance, I gave you the autonomous drive sort of example. There you might need to know, is there a congestion? Is there a traffic buildup? Or is it a crowded region or not? So that's the reason why you might need to want to count, but also locate where the regions of interest are actually falling. So that's the reason why you need instance segmentation rather than semantic segmentation, where you want to have a count as well as you want to locate where these objects are located. Now let's look at some of the examples for medical imaging, right? Like we talked about. So if we look at some of the retinal images, and these are corresponding to your anterior part of the eye. For the retinal images, if we take a look at, let's say, hard exudate, so you see these. So these bright regions, they are typically formed by fat and lipids that have been that have leaked out of your blood vessels, and now they have coalesced in some patterns. So in these cases, you will see that you might need to detect all the regions right? So there are different sites where these yellow regions are occurring. So you might really want to find all the regions and then take a count based off of which you might then say how severe diabetic retinopathy is. The same way, if you might want to actually locate the red lesions or the hemorrhages. So you see there are so many different red lesions strewn all around the retina. So in these cases, counting is actually one of the key tools in order to understand how severe the pathology is. So again, in this situation, instant segmentation will be useful because you'll know is there hemorrhage or not, but how many hemorrhages and where they are located. So that can really help with the treatment process after that. Then there is another use case in which you're using adaptive optics in order to look into the retinal region and count the number of rods and cones. So rods and cones, they're helping you. One is helping you, sensitive to light, and the other one is sensitive to color. So you might really need to look at all of the the cellular concentration in the retinal regions, and then count how many rods and how many cones are occurring. So that's why in that case, whenever you're doing counting and locating objects of interest, in that case, again, instant segmentation can be very useful. And the use case that we will be looking at today, that is using cell nuclei. So if you're looking at histopathology or at cellular level, those images, so then you might really need to figure out where are the nucleuses situated, how many of them are there, and can you really locate each and every one of them. So whenever there is a need to count as well as to locate, you might really need to do that. So the use case we will be looking at is cell nuclei. Right. So now let's see the look at the what is instant segmentation with MaskRCNN. So MaskRCNN, it is just an extension to the two-shot object detectors, which is your faster RCNN. And what it does, so essentially it is just adding another branch to the faster RCNN. So the faster RCNN, it just gives you, it delivers bounding boxes, right? Bounding boxes around objects. What this is doing, it starts from the bounding boxes. So if you have, one image with, let's say, 100 bounding boxes, it will crop off each and every one of those bounding boxes as sub images, and then it will try to fit an object boundary around those bounding boxes, right? So that is exactly, if you have, proper masks, it is actually going to find you regions of interest in and around those, within those, bounding box regions. So semantic segmentation is the most accurate form of object detection. Again, most of the research, that's what it has shown. And that's the reason why MaskRCNN was developed anyways, because, ideally you could skip a region of interest. But if you're doing semantic segmentation, whenever you're taking account of pixel level, there the accuracy or the MAP of the final algorithm actually increases. So what in this case we do is there is an additional loss component which identifies boundaries within the bounding box. So now let's look at the example that I have for you, and I am going to be releasing the code. It is in GitHub for anybody to be able to clone and work off of it. It will be using GPU. And I'm going to be reusing some of the code which is released by MaskRCNN by Matterport. It is currently in TensorFlow 1x. It needs some upgrades if you want to upgrade it to 2x. What we will be doing is we are going to be applying transfer learning. So we are not going to be you're building everything from scratch. We're saying that we already have trained weights, and you can have 3 kind of pre-trained weights. They can be from MS Coco, it can be from the ImageNet data set, or whatever last pre-training you've applied. And then I did want to mention that there's a constant question about which one should I use? Should I use MaskRCNN or should I use UNIT? So that's the reason why I found this very good paper. And this paper I will be linking in the description box below. This actually compares the performance, and again, this is for nuclei segmentation itself, and it compares the performance of MaskRCNN versus UNIT, and then it tries to find an ensemble that is a combination of both of these methods in order to do cell nuclei segmentation. But if you see in most of the use cases, the dice coefficient of UNIT is always higher than MaskRCNN, because MaskRCNN is supposed to do instant segmentation, so it's not really giving you that much importance to each and every one of the pixels, but it's first finding the bounding boxes and then finding your regions within that bounding box. So that's the reason why UNIT, if you're taking dice coefficient as your metric, you will see that UNIT is actually performs better. But if you're interested in knowing how many and where they are located, in that case, you should definitely have, MaskRCNN. So at this point, let's switch gears and start looking into the code. All right, so this is the GitHub that I will be sharing with you all. And again, it will be in the description box below. So the first step to this process is to clone the libraries at this particular Matterport MaskRCNN site. So if you just click on this, you will be able to see all of these files. And this MRCNN, so this is the files that we require, and they need to be stored in the Google Drive where you are going to be connecting your Colab. So the config, model, utils, and visualize. These are the 4 files. These are the 4 Python files which will be used by the Colab that I'm going to be showing you right now. All right. So make sure that you have the first step is always to download this particular MRCNN, and make sure that the MaskRCNN has been co-located in your Google Drive. So now let me show you what my Google Drive looks like. So if I go to my Google Drive, I have this one particular folder, and it is called MRCNN. So this is the folder that I have uploaded. Everything else you don't need, it will automatically get generated as your code progresses, right? So what you want to do is, this is the AIS, MaskRCNN Colab file. So you can just say, open in Colab, and just make a clone. Just copy this particular file so that you'll be able to then run it. So let me show you what my version looks like, right? So first off, you need to do some installation. Like I said, that this is in TensorFlow 1x, so there are a lot of dependencies that have to be met first, right? It is not in TensorFlow 2.0, so please do make sure that you do these downgrades beforehand. All right, so let me just run this. And what this is doing is, this is just reinstalling the correct version of H5PY. After this line runs, it will ask you to restart your runtime, and which is what you should do. You see, you just say restart runtime and say yes, and then you're done, right? The next step, again, you'll have to connect your Google Drive, right? So these are just standard processes, and I've done this in multiple of my videos. If you have questions, please do enter in the comment sections, and I will link you to the other videos where I talk about how Google Drive is connected to your Colab. All right. Once this is done, within Colab, what I have generated is this folder, which is called MaskRCNN. So you see, within Colabs, I have this folder called MaskRCNN, and that is where I have placed this MRCNN folder, right? So that's what I require for usage here, and that's what I am pointing it to. So please do make sure that you change this particular folder to whatever path you are working off. If you do not change this, this is not going to work, right? So please do make sure that this is the path, and these are all the files that are inside. So you should at least have the MRCNN, if nothing else, within this particular location, right? Then I'm going to do some more downgrades, which is your scikit image, making sure that I have SK image 0.16. Otherwise, again, you're going to get some more errors. All right, now I'm just going to be, installing all of the libraries. Now this one cell, this is very useful in order to download the data. As you can see that there are 2 data sets. One is your stage 1 train and stage 1 test. Now I have already downloaded it, so I don't need to redo this. So stage 1 train and stage 2, stage 1 test. Let me show you what the data looks like. So inside the training folder, there is one image. And every single time there is just going to be one cell nuclear image. But then the ground truth is actually every single mask separately. So you see in this case, every single mask contains one of the cell nuclei, right? So if you go to the next one, it will give you the next cell nuclei, next cell nuclei. So as you can understand why this is instance segmentation, because every single cell nuclei is being treated as a separate class altogether. Next, I'll also have to downgrade Keras to 2.1.0, right? And this process can sometimes takes, you probably need to run the cell twice. You see, after I run it once, it says successfully installed 2.7.0, but I wanted 2.1.0. So I'll need to reinstall this. And that's why I have this instruction here, run this twice to make sure you have 2.1.0. Right? So now we have gotten all the different versions. So make sure that you run these 2 in order to ensure you have TensorFlow 1, you have SK image version 0.16 and Keras 2.1, right? If you have these, you are already set, and now you can, go ahead. So first of all, what we are going to be doing is I am going to be, downloading a MaskRCNN Coco. So this is a pre-trained weights, and that's the reason why it's .h5. That is going to get, downloaded. So I'll show you where it gets downloaded. So if I go back to the original folder I'm working off, you see this is the MaskRCNN Coco.h5 that gets downloaded. All right, now what we are doing is we are configuring the data in a particular way, and there are some parameters that you can definitely change here, like the steps per epoch I have at 200. You can change that to something lesser. Then again, the number of ROIs, number of regions of interest. So what's the maximum number of nuclei that you think that can happen in a particular image? Typically I don't think it's going to be more than 500, so that's the reason why we are putting 500. And this is not just nuclei, it could just be any other regions, but they are just not the region of interest to you. They are still foreground region, but it's not the region of interest that's of interest to you. So that's also a possibility. Then there are some of the other functions that you need to reload. So I'm just going to step through these. I just wanted to show you what the data looks like. So the class object that was defined at the top, what that does is it takes this data set that has been packaged in this particular way, which the image and the masks, and now what you're seeing is this is the image ID. The first number is the image ID. The second one is saying 14. That means there are 14 regions of interest in this particular image. So you see these each and every one of if you count each and every one of them, there'll be like 14 nuclei in this image. And then you will have masks corresponding to here I'm just showing you a few examples, but this is just going through 4 random examples, 4 random training images. It's showing you how many total cell nuclei there are, and some of the what the maps look like. So this is just the display function. Once the display function works, then we are going to be loading the model. And what we are doing in this case is we are going to be loading it to do fine tuning, because for MS Coco, the final classification layer, it has 1,000 categories, but now we just have 2 categories. One is background and one is your cell nuclei or not. So we have to modify. You see, these are the 2 different cell categories, pixel region categories. It's either background or it's nucleus, right? And then I just wanted to show you how the training process works, and you can do the training process in 2 ways. First is if you only train the last layer, the classifier layer, again, it's going to be relatively faster. But then if you wanted to train all the layers, then you can just change this layers as all. And again, it's given in this instructions up top, and then you will be able to train it all. So here you see I've completed 200 epochs. It took me somewhere around 1 hour or a little more than an hour to do the complete training. Because again, it's a very large network, so it does take time. And this is the other option if you wanted to do all. So you can just reuse this. Once this model is trained, I'm going to be saving it. And then once the saving has happened, and then we are just going to be doing detection, right? So in detection, what I'll be doing is here, this is a one example of what ground truth looks like. So this is the whole image, and here you see the bounding boxes and the boundaries around them. This is how the ground truth is read by the model, and this would be the prediction that is coming out from it. And you see the prediction is actually pretty accurate. So when whatever is filled in, this is actually your regions that have been detected, and for every single region you will see the probability that it was a cell nuclei is also shown here. So we are publishing everything that is out here. Again, you can choose to change your display as you want, but that is how to read the outcome. Then there is this one function that is also going to show you what the MAP. So in this case, we are only looking at 30 images, and for the 30 images that have at least 0.5 IOU. So intersection over union is at least 50%. In those cases, what would be the MAP? So we are getting somewhere around 67 to 70, 80%. I changed it across a few sometimes it was about 80%, sometimes it was about 67%. So there is quite a good amount of variance if you look at only 30 images. And finally, if you just take at any of the test images, so this is actually the outcome on some of the test images where you are looking at the cell nuclei as well as the bounding boxes around them. So this is how you would take a MaskRCNN and you would modify it to your own data set. And typically MaskRCNN has been the Matterport one that has been released, that is on outdoor images. But here you see how we can reuse this for medical images. I hope this was of interest to you, and this helps. This code helps you work on your own projects. Please do leave me a comment as to how you found, if you think this was useful or not, and please let me know what other models you would want me to cover in the future videos as well. All right, see you next time and take care.